We are going to be talking about network engineering. Yay! It's like a complete opposite of what we just learned about, which is variable fonts, by the way. I had no idea that that existed, so that's going to be a fun thing to play around with. We're going to be going a different way. We're going to go down the stack to talk about stuff which is happening in HTTP. Lots of people are talking about HTTP because it's very performance-orientated. Lots of things are happening there. We're going to be going deeper in this talk, down to transport layer. That's actually my happy place. I really like the transport layer. There's a few reasons we will go into. I know I'm one of those crazy people. Two things before we begin. And some fundamental aspects of network engineering that lots of you are going to know. Some people might not do because of the nature of abstraction. Computer science is based on abstraction. We kind of don't care about the stuff that happens below us, and that's by design. It helps us to evolve, although some of those things have become a little bit difficult in the internet world, and we'll go into that too. Oh, go on. The first thing that we need to know when we're looking at internet engineering, network engineering, is the OSI model. So if you've done any computer science or looked into any network stuff, the OSI model should be relatively, or not new to you, but lots of people don't need to know about it. The OSI model is a very simplistic view of the internet. It helps us to understand how the internet works and to make sure that when we're developing standards for it, that we are sticking to these clearly defined layers. And each layer kind of wraps around a previous layer. So we have the application layer at the top, which HTTP is an application layer protocol. Transport layer sits underneath that. That's TCP. And TCP kind of wraps around HTTP and manages its transport for it. Sorry, my screen's flashing a little bit. Should be okay. The second thing that I want people to understand is that protocols are very, very simple. They are literally a list of instructions. There is nothing else to them. A protocol, as defined in the dictionary, is a set of instructions, and that all is what a protocol is. It's just a set of instructions for two computers to speak to each other. When I started in IETF, I was very, very nervous. I thought this is all extremely complex. They still write all their standards in ASCII and with this beautiful art. It's lovely, isn't it? It's so different from that font stuff that you just had to deal with. It's like it's beauty. One of the things I really like about this, though, is these are just all bits. There's nothing else here. These are just all bits. And this is why it's so easy to understand. There's like a bunch of bits at the top. We're going to make those things do some things. And then we're going to put data at the bottom. This is not difficult stuff. So there's no reason to be scared. Network engineers need to think about a few fundamental things when we're building protocols. One of the first things that we need to have a think about is this. 300 million meters a second is the speed of light. Not quite, it's 297 something million, whatever. It's around about 300 million meters a second. This is a fundamental network limitation. If your content is in San Francisco, the closest that you can be to have 1 millisecond of latency is the next state. You can't get any further than that, that's it. If your content's in San Francisco and you want to try to get 10 milliseconds of latency, the closest you can be is Chicago. I actually think I was a little bit overzealous here. I think it's actually a little bit closer to, just a little bit shorter. But that's the closest that you can get. The reason why 10 milliseconds is quite important to me in the world that I do work in is I do some work in mobile operators with, I don't do a lot of mobile operator standards, but I have to understand a lot of it for what I do. 10 milliseconds was the latency goals for 5G. So that's interesting, given that the whole of the US is bigger than you can actually send data across the 10 milliseconds. Well, anyway, when it comes to generations of mobile networks, every generation is supposed to be a new hardware rollout. So 3 point whatever G, 4 point whatever G will be sort of software rollouts, but new generations are supposed to be new hardware rollouts. To set the requirements for these hardware rollouts, mobile operators get together and they decide on these new hardware rollouts should meet this latency, should meet this bandwidth, should be able to handle this amount of traffic. And then they say that is going to be the requirements of 5G, 4G, whatever. Sometimes a generation's technology previously meets those requirements. And so mobile operators, the big marketing machines that they are, like to say, hey, we got a 4G network. You don't. you have a 3G network that has met 4G standards. It's like, it's okay. We said we got there, we got to the 4G requirements, so we're going to say that we have a 4G network. So even now, I think there are some networks which are still 3G, which are advertising themselves as being 4G, but 3G networks have managed to hit that standard. Anyway, for 5G, our goals are 10 milliseconds of latency for wherever you are. I'd like to see them get to that. One of our, you never know. No, you do really actually know in this case. It's really fun sitting in those meetings. This is also only one way. So if you're making a request and a response, obviously that's going to be more like 20 milliseconds. And also the internet doesn't really work like as the crow flies. This screenshot comes from a website that was trying to advertise some of the pervasive monitoring that was going on in the US. And it was trying to show how many pervasive monitoring like sort of spots you were hitting if you were sending some data from somewhere in Florida to somewhere just inside the Canadian border. But it gives a good indication of these kind of routes that you can take through the internet. I've seen people, sort of routes of people sending data from Canada, which is bouncing all the way around the US before it goes back into Canada. So this is just very common. This is internet engineering. This is obviously not good enough for the things that we're trying to do today, and I'll put this into perspective soon. As so many of the great rendering, performance improvements that we're trying to make are fantastic, but we got some big issues on the internet, which are much larger. One of the things that you can do to improve this situation is use CDNs or edge computing. That is unfortunately something that you still have to do because you just cannot beat the speed of light. And one thing that is always important for you to remember is that there are access networks out there which do some funny things. So even though we understand how the internet works, their access networks don't work in the same way. Mobile operators do not like to think of the mobile network as an access network. Despite the fact that I work within mobile operator world, I do think that mobile networks are an access network because they allow you to access the internet. It's a different architecture, so it has completely different a different setup. It has a radio access network, which is you accessing the base station over the wire. It has a centralized core network. It's completely different to the internet. It uses some of the same protocols, but completely different. So you have this problem with distance, and you're capped by the speed of light. Another issue that you have is the amount of data that you're sending over the network. This is a year old, by the way. I snapped this data a year ago when I was looking for flights for one of my Disney trips, which was fabulous, thank you. It was great, it was such a great time. I had a look in Chrome DevTools. I spent most of my time in the network section, as you can imagine. Here, I know some people won't be able to see it at the back, but a year ago, we had 192 requests on this page and 2.9 megabytes of data loaded up in private browser mode, so it was fresh from the cache. Somebody can tell me why I'm wrong about that later. So these are your two major issues that you've got when designing protocols. Your distance, speed of light issue, and that amount of data which is coming over the network. Now, are the protocols that we designed 30 years ago still applicable to this? Probably not. And this is kind of the problems that we had with HTTP1. So let's have a look at HTTP1. Let's move my mouse out of the way. In HTTP1, we would make a request, and we'd get a response. And then we'd make another request. Maybe that slowly. And we would be waiting constantly for the responses to come back to make another request. This was fine when the internet looked the web looked a little bit like this, where you've got two images and an HTML file, but it doesn't work so fabulously in the web that we have today of 192 requests and 2.9 megabytes of data. And it also does not work fabulously if this data is traveling all the way across the world and back again to get to me. There are some things that developers can do if you're up on that sort of web development layer. Spriting was one of those things, sort of coalescing your resources into one resource, or inlining, or getting all your CSS files to compile them into one CSS file. These two methods are sort of making less resources, so you're making less requests on the network. Another thing that you can do is saving space, so making sure that there's less bytes going over the network. That's what minifying will do. My favorite, I think, developer tool at the moment for doing this is really Service Worker's cache functionality. There's a lot of websites which load the same thing. We were talking earlier about the shell of an application, and serving that down to your users, storing that in a Service Worker cache so you don't have to store it again. When it comes to the mobile network on 3G, I think it's common on 3G to have somewhere between 100 to 500 milliseconds of latency. 4G is less than 100 milliseconds as long as you're close to, near enough to a tower. But 3G is 100 to 500 milliseconds of latency. Which causes some big issues, as we saw earlier. In network engineering, actually, this is one of the interesting things about working across web, internet, and mobile operator networks, is when you tackle a problem like performance, everybody wants to fix the problem with the tools that they have or the things that they know how to use. So there's a phrase that we have in English: if you have a hammer, everything looks like a nail. So for web developers, we always want to solve it with APIs. Let's make Service Worker. Let's do this thing. Network operators like, how can we write? Network engineers are, how can we write protocols to improve this situation? Mobile operators mostly want to do edge computing. Another topic for another day. So one of the things that the network engineers did with HTTP1 is to look at pipelining. I thought I missed an I then, I didn't. Is to look at pipelining. So this is not really a protocol solution, but more opening up extra connections. So we're going to look at our internet connection in a slightly different way. We're going to imagine that our internet connection is a road that takes us from our home to the supermarket. It's just one road, and all the cars are stacking up behind it. We'll call that the TCP road, and it's taking us from our home to the supermarket. Pipelining is opening up extra lanes on that road. So it's just opening up more TCP connections so that we can do more requests and responses concurrently. This means I'm not sending one request and just waiting for that response to come back to send another, but 6 connections are doing that. So I've got a lot more of things going on at the same time. 6 is a number that I think people picked out of the air and worked. I've heard that it's mostly 6 that people do, that browsers do when it comes to pipelining, but I think it could be more or less depending on what their statistics are showing them. The disadvantages of this are more cleanly shown in Jana Iyengar's slide. Jana is one of the QUIC editors, so we're going to be talking about QUIC a little bit later on, spoiler alert. And one of this slide in particular really showcases the negative aspects of pipelining. When you do pipelining, you are opening up multiple TCP connections and multiple TLS handshakes if you're doing HTTPS. So you're sending so many bytes down the wire, waiting for so many round trips, just so that you can send more requests at the same time. And it's actually very, very expensive. This slide shows how many round trips we would have to make with HTTP1 running over TLS to set up an HTTPS connection so that we can just start to send a request and get a response for a web page. You have to do 1 round trip for TCP connection, 2 round trips for a TLS connection, probably 3 if you've not gone to that server before you can send any data. We were saying earlier that 3G connections, you have somewhere between 100 millisecond latency to 500 millisecond latency. And then you're doing that 4 times before you can send anything. This is crazy. No wonder some of the statistics that we've seen previously today are like, oh yeah, it'll take 3 seconds for this font to load over 3G. Of course it will. So this was a big issue. Not only for that, but it was a big financial issue for many people too. So I snapped this picture earlier today, sorry, Harry. It's a big financial issue for so many people. If you can improve your latencies on the mobile on the networks, it means a massive financial gain for so many organizations. You're constantly wasting bytes and wasting time. So a bunch of people got together and they thought, you know what, we need to fix this. we need to do something. We've had HTTP for 20 odd years, maybe we need to do something else. But it actually didn't start out as HTTP2, so it's probably not news to many people here. It started out as a protocol in Google called Speedy. And Speedy took this idea of pipelining, and it did this. So I know this is not going to mean much to so many people in the room, but Ocado is a supermarket delivery service. So rather than me driving to the supermarket, I just make an online order and Ocado delivers to me and however many other people in the area that the van delivers to. So this is sort of a metaphor for multiplexing. So we're taking those 6 pipeline connections and we're going to multiplex them over one TCP connection. And the fabulous part about this is then we only have to make one TCP setup. We're only doing that TCP handshake once. So this is the major gift that Speedy gave us, is taking off all those bytes off the network and making sure that we get there faster. One of the other really cool things it did was header compression, which sounds very silly. But in mobile operator land, people refer to people like me as netheads. I think it's a derogatory term, but I mean, I don't find it to be derogatory, so I'm okay. I think you've got radio heads and net heads, and radio people like radio access networks, and network people like me are with the net heads. And they used to always laugh that HTTP had text-based headers, which was great for debugging because you could just look inside the packet and understand exactly what it was doing. But was really, really bad for performance because you're just sending text over the network, which was taking up loads of space, like 100 kilobytes of space. It was just going over the network, just, for every single HTTP connection. Speedy offered header compression as well. Around August 2014, a lot of browsers started deploying Speedy until the people from Google decided to take this into the IETF and work with a few other browsers on standardizing it. The IETF is the Internet Engineering Task Force. So, no membership is required if you want to come and join us. It's a fun place. They set all the standards for the internet, so it's anything from IP up. The W3C obviously does all the web-related stuff, APIs, JavaScripty things, HTML, DOM. Wow, that's contentious recently. But the Internet Engineering Task Force is where we do all of the protocol work. Those guys started working on HTTP2. When they got together, they did actually decide to use Speedy as a base for their HTTP2 work. There was actually a bit of a debate about that for some time. They were wondering whether to take the goals of Speedy and use that as the goals of HTTP2, or whether to take the work that Google had done with Speedy and build on that, and that is what they decided to do. Evolving protocols on the internet is incredibly hard. So what they wanted to do with HTTP2 was maintain the semantics of HTTP, but change how it was transported. Let's not change too much of the semantics, just how it's transported. So they took the multiplexing and the header compression, which gives the major benefit of allowing us to send multiple requests before needing to wait for a response. And they standardized HTTP2. It had its header compression, it has had its multiplexing. Server push was like there, and then it wasn't, and then it was there, and now it's not again. That's an ongoing thing. But the security thing was actually an open debate for a very, very long time. Speedy had TLS built in. The reason why Speedy mandated TLS was because Speedy was having a really, really hard time getting over the networks. Networks are filled with a lot of middle boxes dotted all the way throughout. These are things like firewalls, NATs, these kind of things. And they were blocking Speedy traffic because they just didn't know what it was. When Speedy encrypted itself using TLS, it was able to get over those middle boxes. So that's why it was mandated with Speedy. But with HTTP2, they decided not to do that. But as browsers started deploying it, they were deploying only the encrypted versions. So we could only really use HTTP2 encrypted, even though the spec says that you can use it unencrypted. In practice, it actually meant that we could only use it encrypted. This was a blog post from the HTTP chair at the time, so from 2014, which is explaining exactly this. And it was a long, ongoing topic. It seems crazy now because we argued about this for months, and now with newer protocols, we just don't even think about it. It's like it's a protocol add TLS. Onwards, team. A lot of browsers implemented this, and we started to get some good stats. This was from April 2017 on Firefox. They were seeing 35% of their requests were HTTP2 in April 2017. 29% of the top 1,000 sites were using it, and if you were serving HTTP2 from your site, there was a 90% chance that your users were using it. Fabulous. There was one issue. At a 2% packet loss, HTTP1 was better. This was because of a fun topic that we're going to talk about called head-of-line blocking. So for the really, really good networks, HTTP2 was doing a really great job. Things were improving. But at a 2% packet loss, HTTP1 was better than HTTP2. This isn't fabulous for people who are mobile networks, for a start. If I'm very close to a base station, then my connection's going to be really great. And actually, the mobile operator networks are really good at not losing packets. They try everything they can to not lose packets, which is actually, it's not fabulous for the internet, because transport layer networks, their congestion control works off of lost packets. So if you don't allow the packets to lose, it can't really react. But if you are far enough away from a base station, it's likely that you will lose some packets. And then HTTP1 would be better for you. The other thing is for the long tail, for people who live in countries or places in the world which have a bad internet connection or an expensive internet connection, this wasn't great. So let's talk about head-of-line blocking, because this was one of the main reasons which was causing this issue. Head-of-line blocking is a bit like, we're going to have a little bit of slides which explain this later, but I'll do a little bit of precursor. In a supermarket, lots of supermarket metaphors today, at one point you have to decide in which queue, unless you're in one of the fancy Amazon supermarkets, you have to decide which queue you're going to line up in to pay at the cashier, right? And you're like, which one is it going to be quick? Is this one going to be fast? Is that one going to be, no, I'm going to stick where I am, it's going to be fine. And then somebody ahead of you, I don't know, they found out that eggs are broken in the egg box or something like that. They have to run and get more eggs or whatever, and you're held up. That's exactly what head-of-line blocking is. Somebody in front of you is blocking you from leaving. And there's nothing you can do. You can get out and join another queue if you wish. That doesn't work on the internet. But you've made your choice. You're there, you're almost there, and you're getting blocked. Head-of-line blocking exists in HTTP. HTTP2 largely solved that with its multiplexing, but this head-of-line blocking still existed on TCP. TCP, so we're going back down to the transport now. We've talked about all our application layer down to transport. TCP is an in-order, reliable protocol. So its job is to take packets and deliver them in order and reliably. If a packet drops off the network, it phones back home and goes, hey, I didn't get this one. Can you send it? And it gets sent again. So this is a picture from a Japanese textbook, which I love because it explains it so perfectly. I've never seen it done so well. You don't need to, I guess TCP and UDP, the picture explains itself. We don't need to read the Japanese. UDP, on the other hand, is a protocol which just sends packets. Just sends, doesn't really care. It doesn't care if they're oddly shaped. If they're not going to get there, it just sends it, off it goes. But TCP is in order and reliable. So in our supermarket analogy, we can imagine that we're in a queue to get to the supermarket, car breaks down, and we're just stuck. Just like with the cashier, we're stuck. We cannot get any further. That tears down the whole connection. With HTTP2, it can be even more detrimental because unlike with pipelining, where we had 6 connections, 6 TCP connections, so if head-of-line blocking happened on just a few of them, those would get torn down, but the others would still be okay. But with HTTP2, we now just have that one TCP connection. And if we experience head-of-line blocking on an HTTP2 connection over TCP, the whole thing falls off. So that was why we were experiencing problems with the 2% packet loss. So really, we've done our fun now in the application layer. We've made HTTP2. It's making some gains, but we still have some problems. We have to go to the transport layer. We've got no choice. And so here is where we talk about QUIC. QUIC is a new protocol on the transport layer. It it's a name, not an acronym. I thought this was brilliant. I've been looking at QUIC for so long, and I remember the days where Google put the explainer document together, and they called it QUIC UDP Internet Connections. I never said that because I'm supposed to say that it's only QUIC as a name and it's not an acronym, but it did stand for QUIC UDP Internet Connections. They've gone away with that. It's now just QUIC, all in caps though. I also thought it was quite funny in that in a previous talk, I said, oh, it's not HTTP3, they'll never call it that. Yoav reminded me the other day about me saying this, and actually the QUIC group at IETF with the HTTP group have almost decided that they will call HTTP over QUIC HTTP3. So I wasn't wrong, because QUIC is not going to be called HTTP3, but also I did say that definitely wasn't going to happen, and it did. So there, what are you going to do? In developing QUIC, if you read the specifications, you'll see that QUIC has 3 very clear goals. It wants to be a protocol that can evolve. It wants to increase performance. I mean, there's not really a lot of point in creating protocols if you're not doing that. And it wants to be safe. We're going to talk about all 3 of them in turn. So let's kick off with evolution. Jana Iyengar said, we want QUIC to work on today's internet. This was most poignant to this particular individual for a reason that I'll explain later. But what this means is they wanted to solve this issue, ossification. Ossification is a word that I absolutely detest, mostly because in standards world, we have this really bad habit of using very, very long terms, trying to make ourselves sound really clever or something. And it's a very global community. In standards, we have lots of people participating from all the way around the world. And I didn't know what this word meant. And English is my native language. So I was frustrated that we were using it in such a global community. Ossification is the forming of bones. So when they form and they cannot then reform, or they cannot take a different shape, I guess, that is what ossification is. And we use this to describe the state of the internet. I mentioned earlier about the problem of middle boxes in the internet. When we initially built, I say we, it was in the 1980s, but when TCP was initially built, initially developed, all of the headers of TCP were open. They're still open today. If you see a TCP packet going across the network, it's very easy for you to get inside of it and see what's going on. You can't see the payload because that's likely to be HTTP over TLS, so that'll be encrypted. But you can see what the TCP packet is doing and see its options and those kind of things. On the back of that, a whole industry was built. Loads and loads of middle box vendors. NATs, firewalls, DPI boxes, they make loads of money out of it. TCP optimizers, optimizing traffic. Any kind of enterprise filters. Have you ever triggered your enterprise filter? I used to work at Ericsson, and I had to tell my boss once that I triggered the enterprise filter, the porn filter. Because I used to go to a lot of anime sites, and they would trigger the porn filter. Anyway, so I was just like, boss, I've triggered this maybe about 20 times in the last couple of weeks. And I promise you this, I'm not doing this thing. It's just like, anyway, it was embarrassing. Yeah, it wasn't a really, really happy conversation. So all of those things are middle boxes on the network. It's a massive industry, billions of dollars. Middle boxes do not like traffic flowing over them that they don't understand. They understand TCP. They get it. This has been around for a long time. TCP is 85–90% of the internet. They can see TCP. They get it. Like, oh, yeah, I know. I understand you. Off you go. They understand UDP as well. UDP is quite a well-understood protocol. And so let that one go as well. Anything else? Not really. I don't know who you are. I'm going to block you. There's no way you're getting in. This has caused massive problems for internet evolution because any development on the transport layer largely never got off the ground. I mentioned Jana previously. He worked on a protocol called SCTP, which was actually developed for telecommunications networks, but was a much better transport protocol than TCP. It had all the cool new stuff that you wanted in a protocol. 9 years he worked on it, trying to get it deployed. It's standardized. There are documents on it. It's being improved. It's used on the telecommunications network, but not on the internet at large, because they couldn't get over this problem of middle boxes and ossification. The transport layer itself had become so ossified that the only two protocols that we can really use are TCP and UDP. You can read the SCTP draft if you want. It's not riveting, though. There's better things to read. So cool, all right. So if we're going to play in the transport layer, and TCP is causing us some problems because of header-line blocking, our option then is we have to move to UDP. That's the only choice we have. And actually, UDP is not a bad choice. It's interesting in what it does. It's kind of a blank canvas. It's like a blank sheet of paper. It's like, oh, you want your packets to go from here to here? Cool, I can do that. I ain't going to do anything else for you, but I can do that. So some people say that UDP is not really a transport layer protocol, mostly because it has no logic. It has no reliability. It's not really a good transport. It's just kind of throwing things over there. But what it does allow in this particular case is a blank canvas for us to build up on so that we can start to build something else which can solve some of the problems that we have today. So that was the evolution. And let's move on to the performance. So we have UDP. That's the protocol that we're going to build on. But TCP had a lot of great logic in it. And we still need to make our protocol reliable. And we still need to get packets back in an order when they get over to the other side. So that logic has to go somewhere. So if you look at a QUIC stack, it looks a bit like this, almost. There's a fundamental change, which we're going to look at in a minute. QUIC has kind of like shoved itself in there, in between the application and the transport layer. It is a transport layer protocol, but it's sort of bulked itself up and it's doing a few extra bits and pieces. QUIC will handle its own congestion control, so it does all of that stuff itself. And it has baked-in crypto in it. In the early days, Google had created a particular crypto, QUIC crypto, maybe it's called Google crypto, which had baked into QUIC. There was a bit of a furore at the IETF regarding this, because Google started rolling out QUIC as a protocol way back in, I think 2014 they were doing this. I don't know, I think it was 2014 they said that they were going to start, and it was sort of later towards the end of 2014, 2015. But what was interesting is if you were using a Google browser and going to a Google entity, like Chrome going to YouTube, what was being displayed in the URL bar was a HTTPS. So your understanding is I am using a standardized protocol over a standardized crypto. But if you looked inside the dev tools, you were actually finding that you were using QUIC. So you were using QUIC crypto. That's not what it says at the top of the bar. So for so many people, they're like, we're really happy you're doing this experimentation. Thank you for making the internet better. But also, we're really lying to users at the moment about this. There was some shouting. That was not one of the ones where I was really involved. It was later shouting I was involved at. So off the back of this, Google took QUIC to the IETF, and they made some fundamental decisions about it. Again, they decided to take it as a base for the work that they would be doing, but instead of using Google Crypto, they would use TLS 1.3, which is a standardized. They were working on it currently. It was about to be done. Give it 12 months. But we'll bake that in instead of Google Crypto. We'll talk a little bit more about that later. One of the things which make QUIC work so well and helps it to beat that head-of-line blocking problem is streams. Streams is it's not really a technology. Streams is a thing. It's a thing. Streams are a thing that we use in HTTP2, which helps beat head-of-line blocking. We're doing exactly the same thing-ish here in QUIC. In a TCP connection, it's a stream of ordered packets. With QUIC, we sort of break those things out into multiple streams. Then we can sort of coalesce them. We can multiplex them over one UDP connection. So it's not very difficult to understand exactly how streams work. But after you start thinking about streams that are in frames, that are in segments, it can get a little confusing. But very, very simply, this is how they work. With HTTP over QUIC, you take streams from HTTP, you take streams from QUIC, and then you multiplex them over one UDP connection, and that is effectively how HTTP over QUIC works on a UDP connection. This beats head-of-line blocking, so yay, that's gone, and we're also multiplexing, so yay, we're saving lots of bytes, we're not setting up extra connections, and not doing a whole load of extra work. One of the other core aspects of QUIC is connection establishment. And connection establishment is not fun. Connecting to another computer on the network, connecting two endpoints on a network, tends to come with a bunch of sort of necessary communication. So one computer say hi, and the other computer says hi. Can I send you some data? Yes, you can send me some data. Cool, I'm sending data now. Okay, thanks. This is the protocol connection establishment. As I mentioned earlier, round trips are really evil. If there's two endpoints are so far away from each other around the world, that you two like just nattering yourself about maybe you want to send data to each other is taking hundreds of milliseconds of time to actually get that connection set up. In the olden days, like I told you guys previously, it would be about 4 times to get 4 round trips to get a connection set up with HTTP1 over TCP. But with QUIC, with TLS 1.3, we can do much better. With QUIC over TLS 1.3, or with QUIC with TLS 1.3, if we need to do a quick version negotiation, we do 2 round trips. If we need to do version negotiation. If we are just going to set up a new connection to a server that we've not visited before, 1 round trip. Awesome. If you visited that server, no round trips. Natasha, how is this possible? Well, you send some data in the first request. So that's how it counts as no round trips. That first set of data that you send in that first round trip needs to be a bit of the data that you don't need to definitely be cryptographically secure, because that first packet has some issues. Sorry, this is moving a little bit. So this massively solves this issue. I like this slide from the IPv6 company. They did some statistics that they presented at IETF. It shows the comparison very, very nicely. So you see here the TCP back and forth, which is two round trips, 4 if you're running with TLS. But just that, look at that QUIC one. Oh, that's beautiful. You gotta love that. 100 milliseconds, that's brilliant. The internet can be unreliable. This is your final bits of the performance aspects of QUIC. The internet can be unreliable. Stuff gets lost and networks get blocked. Let's check the time, we're doing okay. These are 2 things that are investigated in the QUIC recovery draft. If you want to delve into all of the standards related to QUIC, there's a document called QUIC recovery, and it looks at these 2 things, loss detection and congestion control. Sorry, let me move this and see if that makes a difference. Probably not. Loss detection is when a packet gets lost on the network. Congestion control is naturally when they get blocked. Watched a YouTube video recently of somebody looking at the signage in Bank Station in the London Underground about how they manage their congestion control and how they have variable signs to send people around longer routes of Bank to make the congestion control work. So, it's a bit like operator networks. It's fun. The difference is with the London Underground is they control the whole network and the endpoints. When you're dealing in internet, you don't have that luxury, so you have to do things a little bit more clever. With loss detection, though, there's 2 ways to measure loss in QUIC. One is what we call ACK-based, the other one is called timer-based. With ACK-based loss detection, it's a bit like you sending one of your kids down the shops to get chocolate for you or something like that. So imagine you've got a few kids. You need more than 1 kid for this example. So you've got a few kids, and yeah, so we might be saying goodbye to one of them. Your kid goes down the shop, and the shop is 5 minutes down the road, and 15 minutes goes by, and your kid isn't coming back, and you're looking at your watch going, I know how far away the shop is, and I know he knows where the chocolate is, and he's not back yet. So you wait another 10 minutes, and you're like, I'm just going to have to call it. It's lost. It's a lost kid. So, Zach, you need another kid for this one to work. So that kid's gone by whatever, and so you send your other kid, off he goes. So this is what ACK-based is. It's the QUIC protocol knows through the acknowledgements that are coming back what the round trip time is on the connection. And based off of that, it will say, okay, I'm going to give you some time, a little bit more than the round trip time. If you're not back by that time, I'm going to send another one. The timer-based one is just a simple timer. It will run out eventually and then send another packet. For crypto packets, it's extremely aggressive. And it's extremely aggressive because crypto's packets are the ones that are most likely to get attacked. So it will send another one really quickly to make sure that it hasn't got attacked. There's also a tail loss probe, which I quite like on the timer side. Apparently, the last packet is the one which is most likely to be lost, statistically speaking. It makes logical sense as well. So they have a tail loss probe that if once that timer has run out, it sends one to say, hey, did you get the last packet? And it will resend then, if it doesn't see it. Congestion control in QUIC is TCP-like. It actually uses TCP new Reno, if you want to look it up. The way it works is it does what, and you'll see this in Yoav's slide deck as well, because I know he's going to talk about this a bit, so I'll just gloss over it. TCP congestion control, it starts by sending a little bit of data. And then it's like, cool, that bit of data sent, awesome. I'm going to send a bit more data. And they're like, cool, that data got sent. I got an acknowledgement for that. I'm going to send a bit more data. Okay, cool. I'm going to send this massive amount of data. No acknowledgement comes back. Okay, that's lost. Okay, I'm going to half that window of data. So what it's doing is it's sending more and more data, testing the network to find out how much it can send before it gets a lost packet. When it gets a lost packet, it halves its time. It halves the size of the packet that it's sending. After that, it will continue to increase gradually. It's exponential in the start. After that, it's gradual. This seems a bit weird. Like, why don't you just find out what the round trip time is and just send? Oh, sorry, how much you can send and then just send at that. But networks change. You only know your own network, the network that you're on. Anything could be happening once you exit your ISP or once you exit your access network. You've got no control over that. So statistically, this is what works. Eventually, it creates what we call the TCP sawtooth. If anybody ever tells you what TCP sawtooth, asks you about TCP sawtooth, this is exactly what it is. So you'll see halfway through this connection, there's something happened in the network which caused the window size to half again. So maybe some more people entered into the network, the cell got congested, something like that. Finally, our safety aspects. So originally, QUIC had Google Crypto. That got switched out for TLS 1.3. There was a few reasons why TLS 1.3 was the one that got switched in. It was standardized and researched, but also because of this zero round trip time that I told you about earlier. That zero round trip time is so valuable to QUIC, and we'll talk about that when we get to the statistics. There it is again, look at it, it's beauty. TLS and QUIC are actually codependent protocols. TLS is a protocol that doesn't actually fit within any particular layer. QUIC is a transport layer protocol. HTTP is an application layer protocol. TLS doesn't actually have a layer that it's really attached to. You could argue that it's presentation layer, but not really. The QUIC and TLS are codependent. And the way I like to think about this is they're almost like a couple that have moved in together. They both have their things that they're good at. And they separate out the jobs, and that's how they tackle living together. TLS handles the handshake because it's got to set up the crypto. It sends and receives messages, and it also does version validation to make sure that we can protect a little bit more against downgrade attacks. QUIC manages the reliability. It manages the order delivery. It takes the necessity of TLS to transfer the data itself on the record layer and does it within its own frames. I have a really nice cheat sheet for TLS if you want it, it's inside the slide deck. We're not going to go through it because there's a lot of great security in TLS, but it's obscure for a reason. The other thing that TLS offers us, or encrypting offers us generally, is security against ossification. I explained earlier that Speedy ran over TLS to manage to get over the middle box problem, to stop middle boxes from blocking it in the network. If we encrypt QUIC, it's much less likely that it will become ossified, which means that we can evolve it later on. So TLS allows us to do that. I found the QUIC drafts were fantastic for addressing security concerns. These are just some of the attack mitigations which are dotted throughout all of the QUIC drafts, not just the QUIC TLS one. And that downgrade attack is the only one I'm going to talk about here. The downgrade attack is where you force a connection to downgrade. Actually, we addressed this earlier on in one of the talks, where you downgrade a connection to move it to a less secure connection. So if I can't make a QUIC connection, maybe I'll try HTTP2 over TLS. And if I can't make that connection, maybe I'll try HTTP1 over TLS. And if I can't make that one, maybe I'll downgrade to HTTP1 and then get attacked. So QUIC actually has 3 places where version negotiation is set. Well, version negotiation is checked, shall I say, to make sure that it is working nicely. Right, I'm going to have to rush through status and stats. The best way to see QUIC running is any Chrome or Google to Google entity, like Chrome to YouTube. Actually, within the specifications at the moment, there's this one bit on QUIC, which is just set for Google QUIC, so that Google servers can understand whether the QUIC version is Google QUIC or IETF QUIC. Google has now actually, yeah, no, it's crazy. IETF has now actually fully encouraged Google to move all the way over to IETF QUIC, so they should be getting rid of this soon, but in the specs, this currently still exists. QUIC deployment started off in sort of early 2015. They went up, and I've seen them talk about this. This is brilliant. They've talked about this, and they said during this time, between December and January, there was a bug, and so we had to turn it off and fix something. And I'm like, are you sure you guys just didn't want Christmas off? Like, it's just like, I don't believe that for a second. Like, you turned off the whole experiment? No, I'm sorry. I think all the QUIC team wanted to go on vacay. And then over here, in August, there was this massive spike of QUIC traffic. That is when they switched the YouTube app over to QUIC. Not YouTube, the YouTube app. That's crazy. That's so much extra traffic just from the YouTube app. That has a lot of users. Around 4 to 7% of internet traffic is QUIC, depending on what you look at. These are both Sandvine statistics, and one of them says 4%, one of them says 7%. It's around about that at the moment. That may be because of sort of some of the issues around Google's entities not really working in China. I know this is Netflix, but I just love this map. It's like Netflix everywhere apart from China and some places in the Middle East. We need to remember when we develop protocols specifically that there is oddities in the internet globally, and that does affect some things. But over QUIC, video rebuffers are improved for YouTube, 15 to 18%. Google search latency is up somewhere between 3.6 to 8%. These are great statistics. But the places that it really matters is in those areas where they have very bad internet connections. On these lower latencies here on the left-hand side, the improvement, so people who have great internet connections is very low. But on the higher latencies, that's when we're really, really making gains. And it's, again, because of this zero round-trip time. These are statistics which came from Google, which came from Jana. He was the one who put these together. South Korea has this amazing internet. If you want to experience really, really good internet, go to South Korea. When I left that vacation, I was so sad. It was so beautiful, that like constant LT connection, like right in the middle of the underground. I still had it. It was brilliant. But it doesn't make any difference to them. But in India, where they really struggle with mobile networks, it's meaning that people who can't watch video on their mobile devices now can. And that is a massive difference and a great market now, because those people are now online. They're able to do things they weren't able to do before. I'm going to have to rush through. So if you want to check out QUIC working on your network, you can look in Google's net internals. You can also run up Wireshark. There's lots of tutorials online to run up Wireshark and see what QUIC is doing on your networks or your machines. You won't be able to see the packets because they're all encrypted. Yeah, measurements are tough. The IETF is actually meeting this week in Bangkok to discuss QUIC. Sadly, they did not rubber stamp it. They did not reach some agreements because of some of the zero round trip time, the zero stream things have been a little bit hard to interoperate. So they're going to be standardizing most likely in the next IETF, which will be in March. They're also going to be looking at moving QUIC over to be working with other protocols like DNS and WebRTC. And with that, and a little bit over, how does this affect me? Just quickly. I will just leave you with one message with how this affects you. Abstraction is really, really important when it comes to computer science. Layer violation is a crime. We do not accept it. It's not sensible for layers to really talk to each other because it creates ossified networks. The best thing for you to do is to measure, take those measurements and report them back to IETF. Remember the OSI model. Just ignore the fact that there was one layer violation with QUIC and TLS. We don't need to worry about that. TLS is not really in its own layer, it's fine. And remember physics. You cannot beat the speed of light. And with that, I'll say thank you very much. I'm sorry for being over.
Nice work. You went through the QUIC stats very quickly. It was, nobody? There's no laughs for that? Okay.
No.
No quickly puns. That's all right. We don't have time for the Q&A stuff right now.
Oh, sorry. That was my fault.
That's fine. So you can catch Natasha. But we do have just one general question. If you've stoked anybody's interest around this, working with protocols or what kind of research is coming out around new protocols and stuff like that, where would somebody go to find research on what's kind of forthcoming, what's being played around with? Are there good conferences or sites or anything? Or do they just join the IETF? And
actually, there's a couple of places at IETF which I think are really amazing to have a look at. There's a group called the MAP RG, the MAP Research Groups, that's MAP, and they look at all of the new research that's coming up, and especially things in application and transport. So IETF is kind of hard to get started in, but if you start looking at MAP, it's a really good place. Yeah, and the other thing is the IETF plenaries. They're actually on YouTube. You can go and check them out. So they would have had one yesterday. So if you really want to know what's going on, you can watch the IETF plenary, but only the first half because the rest of it is financial boring stuff. So just ignore that bit. Skip the second half.
Well, perfect. Well, thank you, Natasha.
Thank you.